Math 1343, Week 10, Video 7, an ANOVA example. Finally. So we've spent 6 videos trying to lay the foundation for analysis of variance, discussing how to use the F distribution, what it is we're actually looking for from a visual perspective, discussing different types of variability. And in the last video where we completed the ANOVA table, we actually calculated what's going to be the test statistic in our first hypothesis test. In fact, we have pretty much all the groundwork laid already for this first example. But as a hypothesis test, it's going to start out pretty predictably. By now, you should know that most hypothesis tests run the same course, the first of which is to state the hypothesis. Well, in an ANOVA test, we are always testing the null hypothesis that all populations have equal means versus the alternative hypothesis that at least 2 of the means are different. And you can always state those means generically, but it's always in your best interest to try to state them in the context of the situation. Concerning the baseball example that we've been dealing with, we're attempting to see if the mean number of hits accumulated is the same for each batting position in Major League Baseball. So we could state the null hypothesis is something like this. The mean number of hits obtained is the same for each position in the batting order. Now, if you wanted to state them in the context of variables, then we would just basically say that mu1 was equal to mu2 is equal to mu3 all the way down. In this case, since we have 9 positions in the batting order, we would have 9 average number of hits. Oops, I was supposed to say 9. So if you want to cop out and give the ease null hypothesis, you can say mu1 equals mu2 equals ... all the way into the end. But again, it's always in your best interest to try to state the hypotheses in the context of the situation, especially if you ever need to use statistics later on in your career. And believe it or not, you may have to do that. All right, so what would the alternative hypothesis be? Well, the alternative hypothesis in general is at least 2 of the means are different, but in the context of the situation, we could say at least positions in the batting order have a different mean number of hits obtained. I guess we could just say mean number of hits without saying obtained. Obtained sounds pretentious, haughty, if you will. If we wanted to state this hypothesis, the alternative hypothesis in the context of mu's, we could say something generic like, I'm going to pick a no alignment there. We could say something like mu I is not equal to mu j for some I and j. In other words, there's 2 subscripts where the mu's aren't equal. But I prefer my hypotheses in the context of the situation. All right, so the hypotheses are pretty straightforward. Null is the means are equal. Alternative is at least 2 of them aren't. So what's the next step? Well, this depends if we're going to do the critical value approach or the p-value approach. By now, if you've been following my videos, you know I prefer the critical value approach, so we're going to do that one first. All right, so what is our next move? Our next move is to calculate the critical value or determine the critical value in the regions. And of course, sketch a picture. All right, so get all this on one line. Not that it matters, but we can, all right. All right, so we're using the F distribution. We already did verify that the F distribution is appropriate for this problem, since each of the sample sizes was at least 30, and since the variances were essentially the same because, the variabilities were essentially the same, since one standard deviation, or none of the standard deviations were twice as big as any of the other. the F distribution will be a right tail test. Black. That line. Here's our F distribution. I'm going to shade in the right tail. Being a right tail test, that means that this would be our rejection region. And of course, on the left of the critical value would be our non-rejection region. To find our critical value, we need to use the F distribution table, which requires a couple of degrees of freedom. And I didn't clarify it, but in the ANOVA table, the degrees of freedom for the groups is the numerator degrees of freedom, because when we calculate the F statistic, when we calculated it as MSG over MSE, when we found the degrees of freedom for this 2 columns back, it represented the degrees of freedom for the numerator and the degrees of freedom for the denominator. Degrees of freedom for the numerator was the number of groups. There were 9 groups or 9 batting positions, minus 1, which is 8. And the degrees of freedom for the denominator is the grand sample size, which was 270, minus the number of groups, 9, so 261. Now, I did not give a significance level, so we're going to use a significance level. Now remember, with our F distribution table, or I should say tables, we first have to pick the correct page based on the significance level, at which point we look up the correct column and the correct row based on the degrees of freedom. Now, in previous videos, if you were paying close attention to the F distribution that I uploaded, the degrees of freedom for denominator only went up to 50. And this degrees of freedom for the denominator is clearly larger than 50. Well, between then and now, I've made a slight adjustment to the F distribution tables that I uploaded in Canvas, and I'm going to show that to you right now. Similar to the T distribution, I added an infinity row. Add it inside of Canvas. 10% significance level is not what we want. We do want the 5% significance level, which is the second page. We have 8 degrees of freedom in the numerator, so we're looking in the middle column on the right half. And we need 261 degrees of freedom in the denominator. But again, this table only went to 50, but I added an infinity row. So if it goes beyond 50, just do that. And I could have put more values beyond 50, but I wanted to keep this table to only 4 pages. All right, so if we go to the 8th degree of freedom column, which is the middle one over here, and the infinity row, since we've gone beyond 50, our critical value is 1.9384. 1.9384. Excuse me. 1.938. And there's our critical value in the rejection regions. So what's our next step? Well, in the critical value approach, our next step is to calculate the test statistic. In an ANOVA test, this is from the ANOVA table, the last value calculated. And I'm not going to redraw the entire table because we did that in the previous video, but I do have the final result for it. And so from the ANOVA table from the previous video, the test statistic is F equals, got it written down here, 61.6809. All right, so normally this is where you would have to slow down and do some calculations, and we'll do one more video after this where we do a complete ANOVA test. But we already have the test statistic from the results of the ANOVA table in the previous video. So what's next? Well, make a decision. Now remember, in the critical value approach, the decision is based on whether or not the test statistic lands in a rejection region or a non-rejection region when you drew the picture for the critical value. So let's go back to that and remember that our F statistic is 61 and some change. Yeah, I think it's safe to say that our test statistic kind of falls to the right. Oops. Our test statistic kind of falls to the right. Our test statistic was F equals 61.6809. So it does fall just a little to the right into the rejection region, which means that our decision is to reject the null hypothesis. Let's be formal here. Since the test statistic lands in the rejection region, reject the null hypothesis. I do want to remind you that when you're doing this on a homework or a test, you don't have to say all this. You can just say reject the null hypothesis, and that would be perfectly acceptable. I was just reminding you of the reason why we reject the null hypothesis. Okay, so now that we've done that, what conclusion can we make? At no point did I actually pose the ANOVA test as a problem. We just kind of jumped into it. But in general, your last move is to answer the question. And no question was actually provided, so let's go ahead and provide one real quick. Do these samples provide sufficient evidence that at least two different, let's ask the positive question, that all batting positions produce the same number of hits? So we reject the null hypothesis, so we accept the alternative in this place. And recall that the alternative hypothesis was at least two positions in the batting order have a different mean number of hits. So the answer to our question is the samples do not provide evidence. Oops. That all batting positions produce the same number of hits. To the contrary, they provide evidence that at least two batting positions produce different numbers of hits. So we can't conclude all the means are equal. We conclude at least two of them are different. Now, one thing ANOVA doesn't do on its own is tell you which two it is. In the next series of videos, we'll do something called post-ANOVA analysis, where if we've done an ANOVA test and we've concluded two means are different, then we can do either a hypothesis test or a confidence interval on two specific means to see if those are the two that they are. And usually it's the ones that have the most extreme means, the highest mean versus the lowest mean, but you can actually check in pair of means. All right, so we're going to do one more video where we take a data set and we do an ANOVA table and we do an analysis of variance tests from scratch. And that will wrap up this series of videos. In the video, when you're running a Zoom session, there are things that you see as a presenter that you guys don't see as the attendees, so kind of get in the way sometimes.